I'm back here working through chapter summaries for matter and interactions. I'm on chapter 21, patterns, fields, and space. This one is a doozy. I just want you to know, a doozy. Okay. And it's not really bad. It's just three-dimensional, and you got to think about things in different ways. So really, it's about two things. One, electric versus magnetic field, but it doesn't tell you the whole story. And the other thing that we're going to get to is Maxwell's equations, which are really key, but they're going to be wrong, right? So we're going to start with Maxwell's equations, but we're not going to finish them because there's some other things that we need to do to change them. I'm going to give you Maxwell's equations at the end of this, and it's going to be good. So remember, this is the electric field due to a point charge at, a positive point charge. Here's the magnetic field due to a current, and it makes this different shape. And we want to try to quantify these shapes. So we've already have something that we can do with this. We could do a line integral. We've already done that, and I'm going to review that. But the other thing is, how do we deal with three-dimensional spaces like this? And that's the thing that we're going to first introduce, is the idea of flux. So flux is something that comes up again and again, and it's basically how much field passes through an area. So let me just write down the flux for a constant field. Imagine that I have an electric field, and I have some area like this. It's a square, it's an area, and I have an electric field like this, E. I'm going to define the flux through that surface as E dot n hat times A. So flux is the flux, phi is the flux, E is the electric field vector, n hat is a unit vector perpendicular to the surface, and then A is the area. And so this is important, right? It's a lot like, I like to think of this as like rain. Imagine how much rain, let me get another, I'm going to use this. I have here a demo to show something, but imagine I have this card, and I want to say, well, how much rain hits this card? What's the rate of rain hitting this card? Well, it depends on a couple things. How big is the card? How fast? That's like this. How fast is it raining? That's like the electric field. But it also depends on the angle between the electric field and the rain. I mean, the rain and the card, right? Because if I have the card like this and it's raining down, and then I take the card like that, I'm not going to have as much rain. And this dot product here, remember the dot product depends on the angle. You're going to get the greatest dot product when these two are in the same direction or opposite directions. So n hat is a unit vector perpendicular to the surface, right? So I put these pens through here so you can see that's the direction of n hat for the surface. It's perpendicular. It's not in the plane of the area because we couldn't define it that way. Now, you'll notice that if I have a bent surface, they have different directions for n hat, right? But we're dealing with a flat surface here, and that's how we can calculate the flux. Let me jump over here and show you a couple of animations for the electric flux that I did in Python, and I like them, so you're just gonna have to like them too. And I could spend a lot of time on this. I don't want to, but here is a point charge right there, and this is a surface that I break into smaller squares, right? Because there's not one flux in this case, because the electric field changes in both magnitude and direction over the surface. But those yellow arrows are the electric fields. And then you could calculate the flux by breaking this into small pieces. And this would be a difficult calculation for this course, but it could be done. And I probably should have closed those blinds because it's really bright behind me, but that's fine. Okay, let's see. What else do I have here? This is the electric flux. What if I have a closed surface? And I'm going to show you this in a little bit. If I have a closed surface, in this case, I am coloring the flux. Red would be a positive flux. Blue would be a negative flux. So imagine that n hat is this way and E is that way. Then the electric field's penetrating into that surface, and it would have a negative flux. And if it's leaving the surface, it'd have a positive flux. So in this case, you could calculate the total flux just by breaking into squares, which we will do later. No, we won't. We'll do another case. But you can see that the total flux in this case would actually be 0. That's important. Here, what happens if I have two charges inside of a box? Well, part of it's positive flux and part of it's negative flux, but you guessed it, the total flux would be 0 if the charge inside has a net charge of 0. Okay, we'll get to this in a little bit later. Let's go back to the paper, and I'm going to do that problem over here. So this is the flux for a single surface, but what we really want is the flux for a total surface. And if we have finite pieces, let's say we have a box like this, then I can calculate the flux on each side, and the total flux is just going to be the sum of these. We write this as the sum of E dot n hat, and I'm going to write this as delta A, because these all have different n hats and dA. So on each side, n hat would be that way and that way. So I had to break this up into 6 pieces in order to calculate the total flux. Now, what if I have a non-discrete surface? What if I had a sphere? Well, then I could imagine taking the flux over a sphere by breaking this into a bunch of tiny little pieces and then adding up, and I get an integral. So this is important. I'm going to go ahead and write down a very important thing called Gauss's law. And I never know if it's apostrophe S or just apostrophe, but I'm going to write it down and then I'm going to explain it. This says that if I find the flux over a closed surface, that's what this is. This is a surface integral over a closed surface. So it's the same thing as this, but an infinite number of pieces that are infinitely small. And we're not going to do it because we're not going to do it for anything complicated like this, even though it's actually easy. Well, we'll do this one. We'll do this only for trivial cases. But if I calculate the flux over this whole surface, and it's going to be equal to the total charge inside of that surface divided by epsilon naught. And this is Gauss's law. So let's go ahead and do this. I'm going to show you Gauss's law for a point charge and a sphere. So let me go back to my Python code over here, my animations. And here we have, oh, that's not the one. That's fine. Here we have the electric field due to a point charge. Not that. Sorry. Switch. Where's my thing? Okay. The electric field due to a point charge. And you'll notice that there's some symmetry here. We can only really use Gauss's law effectively if there's some type of symmetry. But there is symmetry here because the electric field always points away from the charge, and it is constant magnitude depending on the distance, if you set the distance away. So if I think about all those electric fields the same distance away, then I'm thinking about a sphere. So here is a spherical surface. It's not a real surface, but it turns out that this is not a difficult thing to calculate the flux over because the electric field is always pointing in the same direction as n hat, and it has a constant magnitude. So let's write down Gauss's law for this situation. If I can just switch back over here to the paper. There we go. Okay. So that's important. You're only going to do Gauss's law. You're only going to use Gauss's law for symmetry situations. I mean, you can use it anytime. You're not going to do it for a cube, but you could use it for symmetry. So if I have a charge Q right there, and I draw a sphere around it of radius lowercase r. So over here, the electric field is that way. Right here, the electric field is that way. Right here, the electric field is that way. And at each one of these directions, n hat is perpendicular to the surface such that E dot n hat is the magnitude of E. Right? If those two are in the same direction, n hat has a magnitude of 1, but if they're in the same direction, you could write this as n hat cosine of 0, right? Because the dot product is the magnitude of the two vectors times the cosine of the angle between them, which is 0. And that has a magnitude 1, so I just get E. So that makes my surface integral pretty easy. Let's say the flux is is equal to the closed surface integral of E dot n hat dA. Well, E is constant. E dot n hat is constant. It's once I do that dot product, I can find it's constant, and I can pull that out front. And I get E times the integral of dA. Well, if I want to integrate over the surface of the sphere, what's the surface of a sphere? I mean, we don't need to integrate it. We can look it up. And it's actually going to be equal to 4 pi times r squared, right? The surface area of a sphere is 4 pi r squared. So E 4 pi r squared. And that's going to be equal to, according to Gauss's law, the charge inside, which is just this one charge q, divided by epsilon naught. Now I'm going to solve for E. So I get E equals 1 over 4 pi epsilon naught q over r squared. And that is indeed the electric field due to a point charge. But it's not the real version, right? Remember, we had this for the electric field. E is 1 over 4 pi epsilon naught q r hat over the magnitude of r squared. That's the real version. This is just the magnitude, because we already assumed the direction in order to find this. We assumed that it was spherically symmetric and pointing away, so we had to assume something about the field in order to use this Gauss's law to find the electric field. So it's kind of a trick, but it can kind of be useful sometimes too. Okay, let's do another example. And I don't normally do examples in this, but this is Gauss's law, and it's really important. Okay, so Gauss's law says E dot n hat dA qn over epsilon naught. Let's do this and find the electric field due to a uniform charge plate. So imagine I have a plate here, has an area A and a charge Q. And I want to find the electric field over here. I'm really close to the plate, but I'm drawing it far away. Well, I have to already know something about the field. And in this case, I know that it's pointing perpendicular to the surface away, and I know that it's constant, right? This is something we already found out, so it's kind of cheating. But now I can pick a shape over which to calculate the flux, and that's what I'm going to do. So let's pick, this is traditionally called a pillbox. So imagine that I take a cylinder and it pokes through both sides like that. And this has a surface area on the top here of, let's call that A1, and it has a length of L. And I'm going to redraw that over here. So I want to find the flux over this pillbox. Well, here, let's call this E, and let's call that E, right? Because I know that the magnitude of the electric field on both sides is the same and perpendicular. And over here, I have E, 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 E. And that's the surface right there. Well, if I want to find the flux, it's going to be flux 1 plus flux 2 plus flux 3. I can break this into 3 surfaces and calculate the flux over all 3 surfaces. So this is 1, 2, 3. So over here, the flux is just going to be equal to the electric n hat is this way. N hat over here is that way. But they're in the same direction. So again, I get E dot n hat is just E. So I get E. And then I multiply by the surface area, which is A1. For surface 2, n hat is perpendicular to E in every single situation. The dot product of perpendicular vectors is 0. So I get plus 0. There's no flux. Imagine that being rain. That's not going to hit the surface. And then over here, I get another E, A1. Because again, E and A are in the same direction. So I get 2 E, A1. Now, that's going to be equal to the total charge inside, which is that charge in that little part where it bisects or intersects the surface. So how much charge is inside right there? Well, that's going to be equal to the charge to volume to area ratio for this is the same as up here. So let's say Qn over A1 is the total charge Q over the total area. So I can put that in and use Gauss's law up here. So there's my flux. I get 2EA1, and that's going to be equal to Qn over A1, which is going to be equal to Q over A1, and they have to divide by epsilon naught right there. And look at that. Cancels. Let's solve this. E equals Q over A over 2 epsilon naught. That is the electric field due to a disk. We found that before. Okay, but again, I want to point out that we only got that because we knew something about the field. Now, you could make the argument that if it's a really, really big plane, the only thing that would work symmetry-wise is that the electric field's perpendicular and constant. You could make that argument, but it's sort of a cheat to do this. That doesn't mean Gauss's law is not super useful. It is super useful. Okay, what if I did Gauss's law for a dipole, which I did before, right? I showed those two charges in a box, and I got 0, right? So if I put a positive and a negative right there, and then I put some surface around there, which you can't see, I get the flux of 0. I have to, because the total charge inside is 0. And what also makes the same shape as a dipole? So here I have a dipole. And remember, we have electric field looks like this. I'm just going to draw it like this. These are lines. These aren't fields like that. What else makes something just like that? A bar magnet. But this is E, and this is B. Remember, we talked about that before. So that's B. So if the electric flux due to this is 0, the magnetic flux due to this is 0. And if I break this in half, I don't get a north by itself. I get another north and south, right? You can't have a north by itself. So there's no way to get an individual charge. You're always going to have paired charges if you want to think of it. So we can write this as the following. B dot n hat dA equals 0. Because there's no such thing as a magnetic charge that we know about. So this is called Gauss's law for magnetism. Okay. So if you integrate the flux over some closed surface, you get 0 for the magnetic flux. That's that. Okay. I'm going to do this a little bit backwards. Let's revisit the loop rule. Remember, if I have a charge Q right there, and it makes an electric field, and it doesn't matter what we see, if I now integrate around a closed loop, let's do a circle because it's easy, the integral of E dot dl, where this dl is the direction, is 0. This is the same thing as negative delta V, right? The change in around a loop. We already said that. E dot dl around a loop is 0. We've already done that many times. That was our loop rule. But what if we switch over to magnetic fields and we do the same thing? So I'm just going to switch to right here. Let's just remember, what does the magnetic field due to a moving charge or a wire look like? It makes this different shape of field. This is what the book calls a curly field, and I like that term because the magnetic field is always pointing in the same direction. So let me draw that on the paper. And let's do B dot dl. So here's my wire. Let's suppose I have a current I coming out of the page, and it makes a magnetic field like this. And now I integrate B dot dl around the loop. Notice that B and dl are in the same direction, whereas here B and dl are perpendicular. So E dot dl is 0, B dot dl is just B, right? So this is a different shape of pattern. So if I do this is an important one right here. We're going to change that. Don't put it right there. If I do integral of B dot dl around a closed loop, that's what that means, a closed loop, then I get mu naught times I n. And this is Ampere's law. And again, we can use this in special situations if we know something about the symmetry to find something about the field. Let's actually do that in this case to find the magnetic field due to a long wire. So let's say this has a length of r, and if I know that the magnetic field has a constant magnitude the same distance away, and I draw this circular shape, then I can easily integrate B dot dl, because B dot dl is just B, but B is constant. So B dot dl is going to be B dl. So I can write this as B times the integral of dl equals mu naught In. And here In is the current that passes through this surface area bounded by that curve. I didn't say that earlier. Well, now I just have to integrate dl around that loop. Well, it's just a circle. So I get B times 2 pi r equals mu naught In. If I solve for B equals mu naught In, which is just I, over 2 pi r. And that's what we got before. That's the magnetic field due to a long straight wire. Okay? So let's just show where we are right now, because we've created 4 equations that are incomplete. Some of them are incomplete. And these are Maxwell's equations so far. And I want to point this out because we're building them up, and this is super important so far that what we have. We have this, E dot n hat dA is Qn over epsilon naught. This is Gauss's law. This says that electric fields due to charges make this shape. That's what this really says. This is an electric field due to a point charge. And then I have this, B dot n hat dA is 0. This is the magnetic version of Gauss's law. This says that there are no magnetic monopoles. And then I have this, the integral of E dot dl equals 0. This is the loop rule. Okay, and notice that we're drawing this as a circular loop. This is a surface integral. I know it's a surface integral because that's dA. That's my integral. This is a line integral because that's dl. Okay, and these are vectors. If you didn't have that n hat there, you'd have a really difficult integral because you're integrating over a vector. But E dot n hat is a scalar, so that makes it easier. But that's this is actually going to be Faraday's law. We haven't fixed it yet, so we need to fix that one. I'll put a circle around that. And this is Ampere's law, B dot dl equals mu naught In. So this one's fine and this one's fine, but we're going to need to change this. So let's put an asterisk by that. And we're going to need to change, both these are going to be modified because they're not complete. But you see the symmetry here. We have a surface area integral for electric and magnetic fields, a line integral for electric fields, a line integral for magnetic fields. There's a lot of symmetry going on here, and it's going to get even better, okay? But that's how we're going to start with Maxwell's equations. The end.